Okay, so we're going to move along to continue on with section 4.7. So we got section 4.7 continuing on. We're going to look at example 3, which is going to have us go through and optimize price on a housing unit. So we say all units in a 30 unit apartment building So all units in 30 unit apartment building are rented out when the monthly rent is $1,000 a month. Are rented out when rent, we'll say R equals $1,000 per month. Okay. Every time you increase rent by $40, a person moves out. So every time rent increases by $40, someone moves out. Okay, let's see, what else do we have? Each occupied unit costs $120 per month. $120 per month maintenance. And we want to see what rent maximizes profit. So what we need to do is we need to come up with an equation of profit in terms of rent. Then we need to come up with what is an interval on rent that makes sense. Then we'll find critical points, and then we'll check the endpoints of the interval to the critical points, and we'll see who yields the highest profit. So profit has to be in terms of rent. So I'm going to use P for profit, R for rent. So what we're going to do is we're going to figure out, at a given rent, how many people are in the unit, and then we'll multiply the number of people in the unit by the rent minus the $120 maintenance. So what we need to do is we need to figure out, for this we need to figure out given rent. So given rent are how many people in apartment or living in the apartment. And then we're going to multiply that by the rent. And we have to take, so you make the rent and profit from each person, but you lose $120 for upkeep. So the net amount is the rent minus the $120 per month. That's the profit you make off of each person. So we just need to come up with, given a certain rent, how many people do we have actually in the apartment? Let's think for a minute. So if we take the rent and we subtract $1,000 from it, that would be how much the rent is above $1,000. And if we divide that by 40, this will tell me the number of $40 increases. That entire division. So we started with 30 people because all 30 units were rented out at $1,000. So if we start out with the 30 people and we remove from those 30 people the number of $40 increases, that'll be the number of people that live in the unit, in the apartment. That'll be how many apartments are occupied at a given rent level. So like if rent's 1080 minus 1,000 is 80. 80 divided by 40 says there's two $40 increases, so 2 people moved out. So 30 minus the 2 people says we'd have 28. And from those 28 people, we would earn rent, lose maintenance. So each of those 28 people, we'd get multiply them by the rent they pay minus the $120 upkeep, and that would be the amount of profit we make. So I think this so far looks like it's the right equation. I'm gonna have to take the derivative of this eventually. So I'm gonna first of all I'm gonna figure out the interval. Then we'll go back here and try to figure out, like, I'm probably gonna algebraically FOIL some stuff out and see if we can simplify this to take the derivative. So for the interval that makes sense, we're never gonna charge less than $1,000 because at $1,000 all the units are rented out. So when you increase rent, people move out. If you decrease rent and all the units are all full, you can't get like more than 30 units full. So we're just going to say the lowest we'd go is $1,000, because if we go down to $800 or something, we can't get like 35 people moving in because it's only a 30 unit apartment. So $1,000 the lowest. That's going to be the lower end. On the upper end, we need to say everybody moves out. So we need $30, $40 increases. That'll be the upper end of our interval. So let's see here, 30 times 40. So we need to be $1,200 above the $1,000 starting point. So that would be $2,200. That would be from the $1,000 rent with $30, $40 increases. And at that point, everybody should be moved out of the apartment. So we shouldn't be earning anything. Okay, so we got our interval, got our equation, got our interval. I need to mess around with this equation here to get it set up to take the derivative. Because if I take the derivative in this format, it's going to be a big headache. I think it's going to be easier to algebraically simplify it. So we have 30 minus r over 40 minus 1,000 over 40. All that times r minus 120. Okay, so I'm going to distribute the negative. We get 30 minus r over 40 is the same as 1/40th r. Plus, let's see, what's 1,000 divided by 40? That is plus 25 times the r minus 120. So this will equal 30 plus 25 is 55 minus 1 over 40 times r minus 120. I think we're okay through there. Now I need to FOIL it out. So first is 55r. Outer is minus whatever 55 times 120 is, which is 6600. Inner would be negative 1 over 40 r squared. And last will be positive. It's 1/40th of 120. So I think that's 3. So that'll be 3 times r. So this will be 50, or I guess negative 1/40th r squared plus 58 r minus 6600. Okay, so now I need to take the derivative because I found my interval, so the next step up is find the critical number or critical points. See, 2 comes down, 2/40th, so we get negative, I guess we'll just reduce it in a minute, negative 2/40ths times r plus 58. The negative 660 goes away, so this is going to say p prime of r is negative 1/20th r plus 58. Okay, this is never undefined, so to get the critical point, I'm going to set it equal to 0. I'm going to scoot the negative 1/20th r across, so 58 equals 1/20th r. To get the r by itself, we multiply by 20. So 20 times 58 is 1160. These cancel. That equals R. So this is the critical point. So we have 3 rent values to check our profit function against. We have $1,000. We had $2,200. These were endpoints of our interval. And we have 1160, which is a critical point. And now we need to plug them into the profit function and see who maximizes profit. And then we'll know what rent maximizes profit. So I'm going to use the negative 1/40th r squared plus 58r minus 6600. I'm going to use this this equation right here for my profit. And then I'm going to plug the r's in, the different rents in, and see what profit they yield. So at $1,000, you get $2,640 in profit. $2,200, that's when we did 30 increases, we get $0, which makes sense because at that point we said if we did $30, $40 increases, everybody moved out. Then 1160 gives us 27,040. So this right here is going to maximize the profit. And so it asks us, let me get the little lights to go back on. It asks us which rent maximizes monthly profit. So we'll say rent of 1,160 per month maximizes profit. Okay, so we got that one done. And then we just got one last example to wrap this section up. And then we'll, next section will be section 4.9. So for this final one here, we're going to say for example 4, they want us to design a cylinder. So design a cylindrical can of volume 900 cubic centimeters so that it uses the least amount of metal. So what we're trying to do is we're trying to minimize surface area. Okay, so we got to think about what's a cylindrical can. We got kind of a can like this. It's going to depend on the radius and the height. So we'll say we got radius here. We got height h. Volume is, let's see, what's volume? It's the area of the base, which base would be, if we look at the base of this can, that would be pi r squared. So it's pi r squared times h. That's the volume of the can. For the surface area, which we'll use S. Surface area, you have the area of the bottom, which is pi r squared. The area of the top is a pi r squared also, so we get 2 pi r squareds. That's the area of the top and the bottom. So area of the top and the area of the bottom. And then we need to add to that the area of the side. If I imagine putting like a cut in the side and viewing the side here as a label, when you unwrap the label, that'll create a rectangle whose height is h, and the length of the rectangle will be the circumference of this circle here. So circumference of the circle is 2 pi r. So that would be plus 2 pi r times h. This will be the area of the side. Okay, so we're trying to minimize the surface area. The problem is the surface area depends on radius as well as height. So I'm going to use my volume equation and the fact that they told me that the volume was supposed to be 900. So I'm going to say 900 equals pi r squared h. And I can solve this for h so I can get my surface area equation just in terms of r. So if I get 900 divided by pi r squared, that is h. And then now that I know that this right here is h, so I got h right there, I can substitute that in for h out here. And I can get my surface area in terms of the radius r is 2 pi r squared plus 2 pi r. And instead of h, I'm going to use 900 over pi r squared. The pi's can cancel, and one of the r's will cancel. So we'll be left with our surface area equation in terms of the radius is 2 pi r squared plus 2 times 900 is 1800, all that over an r. So this is the equation right here. This is our surface area equation that we want to work with. Now this is going to be a little weird because we're not going to be able to get perfect closed intervals on these because we still want this thing to be a can. So what can happen is for the interval, the radius could approach 0. As the radius of your can approaches 0, you get basically a very, very, very tall, very narrow can. So as the radius of the can gets closer to 0, the can goes through and gets taller. The other way is the radius could approach infinity. So as the radius approaches infinity, you get a flatter and flatter and flatter and wider and wider and wider can. That's very, very, very small height. So these are kind of the, and every time the radius gets larger, then this thing gets flatter. And on this one, every time the radius gets smaller, the can gets taller. So this is going to be the interval in this case. If we let the radius go to 0, then there is no can. And the radius can't actually be in infinity, but it can approach it. So you get a bracket with kind of open intervals. So this is our intervals to check. Next, we need to figure out what is the critical point of this. So I'm going to look at the derivative of our function here. Let's see, the 2 comes down. 2 times 2 would be 4 times pi times r. This right here is r to the negative 1, so the negative can come down. And that would be r to the negative 2. So based on this, r equals 0 makes s prime undefined. So r equals 0 is a critical point. To get the other one, we're going to set the equation equal to 0 and solve it for r and see what r solves that. That'll get us our other solution. So this will move over, and we'll get 1800 over... r to the negative 2 is the same thing as over r squared. That equals 4 pi r. The r squared will multiply across. So it's gone over here. The 4 pi I'm going to divide across, so we'll get 1800 over 4 pi equals r cubed. So basically the cube root of 1800 over 4 pi is going to be the other critical point. So let's see what that is. 1800 divided by 4 pi. Cube root of all that. And I get that that's about equal to 5.232. The r equals 0, that would correspond to a can with no radius, so it wouldn't actually be a can. So we're going to throw that one out because this critical point doesn't make a can. So what we got is 3 things to check. We have our endpoints here, or we're going to need to view them as kind of limits. So what happens as s approaches these endpoints? What happens as r approaches the endpoints? What happens as r is this value? And we want to think about what does the surface area do. So we'll say, okay, here's our r's. Here's surface area. I'm going to bring the surface area equation down here so I can look at it easier. We'll have what goes on as r goes to 0, what goes on as r goes to infinity, and what happens as r is the 5.232. So we're going to just go through and kind of look at what happens in each of these cases. The surface area equation we were dealing with, I'm going to move that down there so I can look at it whenever I need to evaluate these. I guess we'll put it down here. So as r goes to 0, this first term here goes to 0, and you get 1,800 dividing by something that's going towards 0. When you divide by something going towards 0, that heads off towards infinity. So in this case, as r goes to 0, s heads to infinity. As r goes to infinity, the r squared term runs off to infinity, so the first term goes to infinity. And you get 1,800 divided by something running to infinity, that heads to 0. So you also get s heads out to infinity in both those cases. When r equals 5.232, let me type that in. We get 2 pi times 5.232 squared plus 1,800 divided by 5.232. This gets us the surface area is equal to 516.032. So this one right here, you compare it to something running off towards infinite surface area, running off towards infinite surface area. This one right here is going to minimize the amount of surface area, which means this one right here would have us use the least amount of metal. It said what dimension should the can be to do that. The can should have radius 5.232 centimeters. And then to give the full dimensions of the can, we need to say what the height is also. So to get the height, let's see, where was height in terms of radius? It's right here. So we're going to use this equation right here. So we'll say 900 divided by pi times our radius, which was 5.232. Square that 5.232. That will tell us the height. And the height would be 10.465 centimeters. So these are the dimensions of that can that will minimize the amount of area metal that gets used, because they will minimize the surface area of the can. So that's going to wrap up section 2.7, and we'll stop there.